Sketching the graph of f of x. Objectives. By this lesson, you should be able to sketch a comprehensive graph of any given f of x function using calculus. Basically, this lesson is like the culmination of the last 3 lessons. We're going to use everything we learned. We're going to use stationary points, concavity, increase and decrease function to graph a function. So let's start with this. These are the 4 types of curves we could get when we graph a function. So before we start talking about this, let's backtrack a little bit, right? So we're going to graph f of x. Now remember everything we learned. We learned the first derivative tells us increasing and decreasing, and max and min points, right? We learned the second derivative told us concavity and inflection points, right? We have to know this because that's all we're gonna do today is we're gonna find increase and decrease function and concavity, and we're gonna combine those two to make a graph. So in our 4 types of curves right here, look at this first one. Concave up, right? So it's opening up, but it's decreasing, it's going down, right? So this is where the second derivative is positive, concave up, but the first derivative is negative, decreasing. You go over here, look at this one. Concave up, so it's opening up again, but now it's increasing, right? Notice how these are both opening up. This side's increasing, that side's decreasing. So this is another second derivative positive, first derivative negative. You go down here, concave down, so that means the second derivative is negative, sorry. And it's decreasing, so the first derivative is negative also. See how it's like opening down and going down? Where this one, concave down and increasing, it's opening down, but it's going up from left to right. So this is second derivative negative. That's just bad. Second derivative negative, and first derivative positive. So again, that's something that type of curves we're going to start drawing. When we start drawing stuff, we're going to try to either curve it up, curve it down, make it increasing or decreasing from left to right. Right, like everything else, we're going from left to right. Okay, let's talk about a process of graphing a function. Pretty much is putting everything together, right? Everything we learn, we're going to put it all together. Find and classify all the points where f of x equals 0. Remember, this is how we find our min-max points, where f of x equals 0 or undefined. Let's get our critical points. Right, we're going to get our critical points from doing this. So that's step 1. We're going to find our critical points. Step 2, we're going to do a sign chart with those critical points or to find out where it's increasing, decreasing. So let's face it, critical points. We'll do a little sign chart here. Right, that's to let me know if it's increasing or decreasing. And then also, next step, classify all the points of inflection. It's also to let me know if this is a max or a min. Find intervals where the function is concave up and concave down. Remember, this is a second derivative, right? So we're going to do second derivative. We're going to set that equal to 0 and do a sign chart. Keep in mind when we do our sign charts, we always do a sign chart when we do our test points, we plug it into that derivative. So if I'm doing a sign chart for second derivative, I plug my test points into the second derivative. I do a sign chart for my first derivative, you plug it into the first derivative. And then we're going to sketch with all the features we found, right? Once we found that, our concavity, our inflection points, which I end right here, we just sketch all that. So here's a key thing that's not mentioned. For all these things, if I have a point, like let's say I have a min, at A, you're going to need to find the y value. We're actually graphing this stuff, so we're going to need the y value. Remember, the way you find the y value is you plug it into the original function. So if I have a min at x equals A, I'm going to need to plug into the original function to take my point. So A and f of A. Right? Same thing if I have a max at, let's say, x equals B. Right? I'm going to have to plug it into the original function to actually get the value because we're graphing these functions now. And the same is true if we have any inflection points. If we have an inflection point at x equals c, I'm going to plug it into the original function to get the actual point. So just keep that in mind. When we do a sign chart, our test points go to that derivative, right? So sign chart of the first derivative goes into the first derivative. Sign chart to the second derivative for concavity goes into test points go into the second derivative. When I want the points of the actual points of the graph, and then you plug it into the original function. And that's kind of the gist. So let's do an example. So here's our first problem. So again, our goal is to be able to sketch this. I have a little chart down here. We're going to graph it all onto there. So we're just going to follow the game plan. We're going to do the same thing we always do. We're going to find our critical points, do a sign chart to see where it's increasing, decreasing, and find if it's a min or max. Once we do that, we're going to do our second derivative to find the concavity points. And once we get all of our points and inflections, I should say intervals of concavity and our inflection points. And once we found all that, we're just going to plot it onto our graph and then connect the dots. So let's get started. So step 1, right? Let's find a derivative. So f prime of x is going to be, take derivative, so x squared minus x minus 2. Alright, so that's my derivative. We're going to set it equal to 0, find the critical points. So I could factor that, that's x minus 2, x plus 1. Right, so my critical points are at x equals 2 and negative 1. Now we're going to do a sign chart. Right, so like this, little arrows, negative 1 and 2. Let's put a little infinity sign so we don't forget. Now it's been a little while since we've done a formal one of these, but if you remember, I like to write the intervals first so we don't forget. So negative infinity to negative 1, negative 1 to 2, and then 2 to infinity. Right? These are my possible intervals of increasing and decreasing. What we do next is we pick some test points. Right? Like over here you put like negative 2, 0, and like 3. Remember, now we're doing the derivative. We're doing the first derivative, so we're going to plug it into the first derivative. You can either plug it here or there. I always prefer this one because all you really care about is the sign. If you plug in negative 2, I get negative 4 times negative 1. I'm going to get a positive. Negative times a negative is a positive. Plug in 0, that's actually easier to plug into here. You just get negative 2. So negative. You plug in 3, positive times a positive is going to be a positive. So right, so look what this tells me. I know it's increasing. Right, my graph's going to be increasing from negative infinity to negative 1, so we're going up. It's decreasing from here to here, from negative 1 to 2, and it's increasing from 2 to infinity. Right? What I also know, right, we learned this last lesson, is that at negative 1, it's going from positive to a negative. So that's a local max. We have a local max at x equals negative 1. Now, again, we're doing an actual graph, so I'm going to want the actual point of this. So I got to plug this into I got to actually plug that into the function. Now, I'll save you some heartache with me just doing arithmetic forever. I'll tell you the answer is negative 1 and 25 over 6. Or as a decimal, negative 1 and 4.16 with a line over it, repeating. So that's the local max, right? So keep that in mind. I have a local max right here. That's my point. And then we also learn, right, we have a local min. At 2 goes from negative to positive, so same idea. I have a local min at x equals 2. But again, since I'm actually graphing this, I'm going to want the actual point, so I'm going to plug it in. I'll save some time. That is 2 and negative 1/3. Or 2 and negative 0.333. So now I know where it's increasing, I know where it's decreasing, right? It's increasing from negative infinity to negative 1. From 1, it's decreased from here to here, and increased from there to there. Let's move on to concavity. So now we're going to need the second derivative. So let's take derivative again. 2x minus 1. Set equal to 0 to find my possible inflection points. I get 1 equals 2x. 1/2 equals x. Do a sign chart for the second derivative at 1/2. Again, let's figure out what intervals are. I could be from negative infinity to 1/2, or I could be from 1/2 to infinity. Right, and before we do some test points, we're going to plug in 0 and let's say 1. Again, you can plug it into the derivative. I plug 0 and I get negative 1, so 0. If I plug in 1, we get 2 minus 1 is a positive. Right, so I'm concave up from negative infinity to 1/2, and I'm concave down. There we go. Didn't see the minus there. And then concave up from 1/2 to infinity. And there's a sign change here. So remember, that makes 1/2 an inflection point. So I know I have an inflection point at x equals 1/2. But just like the other ones, I'm going to actually want that point since we're doing a graph. So we'll plug into our original function, and we'll get, and that's going to be about 1/2 and 23 over 12 if I plug it in. Also known as 1/2 and about 1.9. So that's all the information I need, right? I have my local min, my local max, I got my inflection points, and I know my concavity and stuff like that. So now it's time to put it all together into a nice graph right here. Before we put it all together, let's review what we learned, what we have, right? So let's do a little line right here. Put all the stuff we know. Right, I know I have a critical point at 1/2. I have an inflection point at 1/2. So that's my inflection point. I have a critical point, right? Look at 2 and at -1. So if you're at 2, I have a critical point. And at -1, I have another critical point. Right, and then we learned up there that before -1 it was increasing and then decreasing. So this is increasing. Increasing. And between -1 and 2 is decreasing, so both of these are going to be decreasing. And then we also learned, right, that both of these, that before 1/2 is concave down. So this is also concave down and concave down, while these two are concave up. So this is increasing and concave down. So it's going to be kind of like, you're going to be going up, but you're going to be opening down. So it's going to look kind of like this, right? Opening up, but going up, opening down. This one's decreasing and concave down. So it's going to be going down and like this, right? You can see it makes this increasing, decreasing, makes this a max like we did earlier. Over here, it's in our inflection point, right? So it's going to go down. That's a switch to going up. So decreasing, concave up. So it's going to be going down, but opening up. So it's kind of unusual. So it's going to be like opening, it's going to be like this. Right, so it's going down but opening up. And then finally increasing and concave up. So it's going to be going up and increasing. Again, you can kind of see this makes the minimum. The truth is though, if you connect your points correctly, it's going to turn out to be that way anyway. So let's start plotting our points. So we have 2 and -1/3. So 2 and -1/3, so around there. That's my local min. Right, and then we have a local max at -1 and 4.16. So -1 and 4.16. So around there, I guess it's an estimate. It's a local max. And then my inflection point is 1/2 and 1.9, so about 2. So 1/2 and about 2. Let's go around here. It's my inflection point. Now you can help yourself out by doing a y-intercept. Remember, if you want to do the y-intercept, super simple, just x equals 0. So you give yourself another point that helps out. If you look over here, plug in 0, and your y-intercept will just be 3. So this gives you a nice little extra point to connect through. But it's not one of the big points. It's not a big deal. So right there. Now let's put it all together, right? So here's the thing about it. You know that's a max. And before -1, you were increasing. So it's just a sketch. So you just got to go increase until you get to that max there. You kind of want it to be, you know it's concave down, so you kind of want it to be curving down. Something to that effect, right? Then you got to hit that inflection point. So try to get there. Oh, I should have gone through the y-intercept, but whatever. Right? Again, you want to be curving down because it's concave down. And then now you got to hit this thing from the inflection point. Notice again, you're still decreasing, but you should be kind of curving up, concave up. So try to hit it. Curving up like that. And then finally, you're increasing after that, and you want to curve up. And you get something to this effect. And that's your graph. Right? A lot of it's just finding the inflection points, find the max and min, and then just kind of combine the concavity. Let's go to the next one, right? So here's another one, right? Same concept. We're gonna try to classify all these critical points, do all the stuff, and graph it. Right? Just as always, our first step is we're gonna set the derivative equal to 0. So f prime of x equals 12x cubed minus 3 times 6 sucks 48 plus 48. That one's easier. And the 9 goes away. Bye bye 9. Hey, look, there's no constant term in this case. So we have this, right? Now we're going to set equal to 0. And remember, the first thing we do when we factor is you want to see if they have anything in common. That's always the first step for factoring. That should have been 48 also. There we go. Right? And now, in this case, they all have a 12x in common. So we lucked out. Made it a little bit easier. So that's going to be x squared minus 4x plus 4. Right, now you can factor this some more. That still factors. That's just x minus 2, x minus 2. You can split it to get our answers. We're going to have x equals 0 from right here. 12x equals 0 for people that don't see that. There you go. And then right here, x minus 2 equals 0. They're both the same, so you have to do one of them. X equals 2. That's actually considered a double root because you have it twice. So those are my critical points, right? So next up, let's do a sign chart for that so you can figure out where it's increasing, decreasing, if it's a max or min. Right, so 0, 2. Again, let's put the intervals first. So it says negative infinity to 0. If it helps, here's a little infinity sign. 0 to 2, and then 2 to infinity. So those are my possibilities, right? Next step, it's a little sign. Let's pick some test points and plug it into our derivative. So this would be like negative 1, 1, and 3. Plug in and see what you get. Again, you can plug into anything you want. I prefer to plug into this thing. Actually, I prefer I could talk to plug it into x minus 2 squared. Because I know this is for sure positive. Right? It's a squared number. It's automatically going to be positive. So all I got to worry about is this part. If I plug in negative 1, it's negative 12 times a positive, which is a negative. If I plug in 1, that's, again, it's going to be positive because you squared it. And then 12 times a positive is going to be positive. Same thing with 3. Plug in a 3. This is positive. That's always going to be positive, so positive. Right? So we get decreasing, increasing, increasing. Right? And then if we look here, right, at 0, which is one of our critical points, and 2 is one of our critical points, it's going down then up. So it's a min. And then 2 is going up and then up again, right? It didn't change. So that's called a stationary inflection in IB. And like always, since we're doing an actual graph, right, our local min's at x equals 0, but I need the actual point, so you gotta plug it back into the original function. 0 is lucky enough, that's easy. Just plug in 0, you get negative 9. That's a 0. There you go. I have a stationary inflection at x equals 2. Again, I gotta plug it in, not as easy as the other one. But I'll save you some time of me just plugging stuff in it, and you get 2 and 7. That's a 7. Right, so that's my stationary inflection, that's my minimum. So we got the first part done. Now let's talk about concavity. And I'm running out of space. That's not the best thing in the world. Anyway, so second derivative. Right, so that's my first derivative, so take it again. So that's going to be 36 x squared minus 96 x plus 48. Oh, that sucks. Set equal to 0. So I get 36 x squared minus 96x plus 48. I can actually factor out a 96. You can actually factor out a 12 again, but just a 12. Make it a little bit easier. Now again, I got to factor this. It's a fancy factoring, right? You multiply this thing by that thing, and you get 12x squared. Find the combination, I get to negative 8, which in this case would be negative 6 and negative 2. Plug it in and factor. To save you guys some time, I'll tell you right now, it is x minus 2 and 3x minus 2. So my test points are my possible inflection points are x equals 2 and x equals 2/3. If you notice, we have x equal 2 again, right? That happens anytime you get a stationary inflection. It should happen kind of twice. That's why it's inconclusive when you do it, when you get it on the second time, because it's still an inflection point, so you're going to get it the second time. But we already know it's a stationary inflection, not the natural inflection point. But anyway, let's do a sign chart. So I got 2/3. I got 2. Right, my intervals are negative infinity to 2/3, 2/3 to 2. Crap. There we go. I'm not happy about that. 2 to infinity. Pick some test points and say 0. That's easy. Just plug it in. 48. So positive, done. Pick a test point here like 1. Plug it in. I'll say sometime it's 36 plus 40, that's less than 96, so negative. And then plug in something bigger like 3, and I'll say sometime you're going to get a positive. So this is concave up, concave down, concave up. Again, notice it's actually flipped, it actually changed on both of these, so we do have an inflection point at 2/3. And just like before, you got to plug in the actual value. I'll say sometime it's 2/3 and negative 2.5, roughly. Yeah, no, not the best number in the world. And it also changes at 2, but you have an inflection point already. Like, you know, it's a stationary inflection. So I mean, it's still an inflection point. That's why it popped up again. But we already know that. We don't have to put it again. So that's all the information, right? So if we want, we can make a little line so we can make sure we know what we're talking about. Let's put our critical points, which in this case were 0 and 2. So that's my critical points. As I say, right, we had, this was a stationary inflection. This was our min. We have an inflection point at 2/3. So it's an inflection point, right? And what do we learn? We learned that this was decreasing. This was increasing. It was still increasing here also. And then it was increasing the rest of the way. And then from our second derivative, we learned that it was concave up all the way to 2/3. So from here to here, it's concave up. So concave up, concave up. Right, so again, that's going to look like you're going down, but you're concave up. So it's going to look, my head always has a hard time with this one. You're going to be decreasing, but it's concave up. So it's going to be kind of like this, right? You're opening up, but it's going down. Increasing concave up, that's a lot easier, just kind of more natural. Over here, right, these are both, we learned that after 2/3, it's concave down. So 2/3 of 2 is concave down. So that's this little part right here. So this is concave down. So you're increasing, but you're opening down. So you're going up, but you're opening down. So it's kind of like this. Right, those are always the ones that are a little funky. And then after 2, we got concave up again. So it's going to be increasing concave up. Right, so that's the way it's going to look, kind of. Again, that's just like a bonus that helps you draw it. But if you have your points connected, for the most part, you should be okay. But this is to get it like right on. So let's graph this thing. Right, first thing we plot our points. Right, we have a min at 0 and -9. So 0 and -9. I'm just going to make that -9 because it's my graph and I can do what I want. Right, and then we have a stationary inflection at 2 and 7. So 2 and 7. Likewise, I'll make this 2 and 7 because, again, my graph, my rules. And then have an inflection point at 2/3 and -2/5. So 2/3, like around here, and -2/5. So let's say, to make it kind of the same, let's put it right here, kind of the middle, because it's some weird thing. So that's my inflection point. Oh, this is a stationary inflection, that's important. This is a min, also very important. Right, so now that we have all that, it helps if we look down here, and we go, okay, so before my 0 here, it should be decreasing and kind of concave up. So you should be going kind of like a bottom like this, kind of curve down. So it's going to be something to this effect, right? And then from 0 to 2/3, we got to hit the inflection point. So we got to go kind of like this. And then from 2/3 to 2, I got to hit that point, but you should be flipping the other way now. You should just kind of be going concave down. Now, right there doesn't pass a vertical line test, but that's just because I'm bad drawing lines. And then after that, right, we're going to be going up again. Notice, right? It's a stationary inflection. It goes up again. So up and concave up. So kind of like this. And that's your graph. Hopefully yours is a little nicer than mine. But that's the idea. Our next example is going to be actually more of a review problem, just to make sure we have all this stuff set up. We're still going to apply all the principles we reviewed for this lesson, but now we're going to apply it to more of a review problem, just to make sure we got our natural log stuff down. So let's see, find the x-intercept, right? Remember the way we do that? You set y equal to 0. It's always the opposite. You want the y-intercept, you set x equal to 0. In this case, you want the x-intercept, so you set y equal to 0. So here's my y. So we're going to have 0 equals natural log of 2x minus 1 minus 3. So we're going to do a little review of how to solve natural logs, right? You want to get that by itself. So we're going to add 3 to both sides. I get 3 equals natural log of 2x minus 1. The way we get rid of natural logs, take the e to both sides. So you get e cubed equals 2x minus 1. Add 1 to both sides. Equals 2x, divide by 2. E cubed plus 1 over 2 equals x. You simplify that, put in a calculator, you're going to get about 10.1, roughly. So our x-intercept is about 10.1. Or if you want, 10.1 and 0, right? That's our point. Look at B. Can f of 0 be found? What's the significance of the result? So let's see. Let's plug in 0. F of 0, I'm going to get natural log of 2 times 0 minus 1 minus 3. I get natural log, well 2 times 0 is 0. So 0 minus 1 is negative 1. You can't do that, right? Natural log of negatives don't work. The domain of natural log in general, you have to be greater than 0. Right? So that's a negative. Natural logs don't do negatives, they don't do zeros. So no, you can't do it. What's the significance of the result? Well, you're plugging in 0. Kind of just talked about that, right? If you're plugging in 0, that means that's the y-intercept. Right? When you plug in 0 for y, it's the x-intercept. When you plug in 0 for x, it's the y-intercept. So in this case, we have no y-intercept. That's the significance of the result. C, find the gradient of the tangent to the curve at x equals 1. Remember those words? They sound familiar, right? That's the derivative. We're taking the derivative of the curve. Now notice it said gradient of the tangent. It didn't say the equation of the tangent. I don't need to do y minus y1. Gradient just means take the derivative, plug in 1. That's all they want me to do. So let's take a derivative. Hey, it's a natural log. More review. I love review. Right? So natural log, remember the derivative of natural log is 1 over the inside times the derivative of the inside. Right? Chain rule. Classic chain rule. So 1 over the inside times the derivative of the inside, which is 2. The 3 goes away. So my derivative is just 2 over 2x minus 1. They want me to plug in 1. So 2 over 2 minus 1, or just 2. D says find the domain of f. I kind of talked about this already. The way you do domain of natural log, there's some domains you should know, right? Square root domains that we should know. Square root of x, it can't be negative, so x is greater than or equal to 0. 1 over x, can't divide by 0, so x cannot equal 0. And then natural log or log of x, it's x is greater than 0. You can't be negative or 0. So in this case, all we care about is what's inside the natural log. So that part, just like it is over here, has to be greater than 0. So 2x minus 1 has to be greater than 0. Because that's what's inside the natural log. From here we just solve it. 2x is greater than 1. X is greater than 1/2. That is my domain. You can leave it at that. You can put 1/2 to infinity. Either way, it kind of works. They want me to find the second derivative, and hence explain why f prime is concave down for all. Well, remember, just think about this. Why is it concave down? Concave down means the second derivative is negative. So they want me to find the second derivative, and it should be always a negative value. So let's see that. So this is my derivative. Second derivative would be another just quotient rule, right? U prime u over v, which is u prime v minus v prime u all over v squared. I'll do this real quick. The derivative of u is 0. 0 times 2x minus 1. Minus the derivative of the bottom is just 2 times the top 2 all over the bottom squared. And we're going to get, that's a 0. Get away. Negative 4 over 2x squared minus 1. Now again, we got to show why this is always negative. Well, look at it. That's what we talked about. Look at this bottom here. Right? It's squared. Squares are always positive no matter what. So this is always positive. And look at the top. It's a negative. Right? And a negative over a positive is always a negative. So this is always negative. And since it's always negative, I know we always know it's concave down for all x. Concave down for all x is greater than 1/2, which is our domain. And last thing, graph the function showing the features you found. So we didn't find that many features. We just know it's always concave down, and we found the x-intercept at 10.1. Right, so let's go over that again, right? We've only found a couple things, right? We found 1 point, right? That's our x-intercept. We know there's no y-intercept. That's important. We know that the domain is actually greater than 1/2, so we can't go any further left than 1/2. And we know it's always concave down. So how would I graph this? Using the bare minimal stuff we know. Right, I know at 1/2, it have to be greater than that. So there's a kind of vertical asymptote right there, because it has to be greater than that. Other than that, I just know that we hit a point here at 10.1. 10.1 and 0. That says 10.1. Oh man, that's ugly. Even for me. Right, like that. I have to hit that point, and I know it's concave down for all of it. We didn't find it, but it's also increasing. Right, our first derivative here, when we plugged in 1, we got a 2, so that just means it's increasing. Right, it's like we did a sine chart, so it's increasing. So you can start down here somewhere. It's increasing, it's concave down, so it'll be something to this effect. And that's the idea. Again, I care less about that graph than I did about all this like review stuff there. Okay, almost done. Last thing's about graphing. Now, what we did before was I gave you the function, and then you had to find a derivative. We'll go over that to make sure we remember how to do this. But what's new this time is that we're going to go backwards. I'm going to give you the function, I'm going to give you the derivative, and I want to find the original function. Now, think about that. There's not one answer. There's actually many answers. So it's just one sketch of a possible original function. So we're going to do that a couple of times. But before we do that, let's go the normal way, the way we know already. Right? We know if I give you a function, and I want you to draw me the derivative, what we do is we look for the critical points. We go, okay, the critical points here are the max and mins, because I have the original function, I'm trying to find a derivative, right? Anytime you're trying to get a derivative, you're looking for the max and mins. So around here, and around 3, then you go plus, 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 so it's positive, minus, 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 so it's negative, and then plus, 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 so positive. So it's something to that effect, right? And if you want the second derivative, you just do it again, right? You find the min or max, which in this case would be here. That'll be my 0. And then negative, 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 so negative, and then positive, positive, positive. Right? So that's how you go from original function to each derivative, right? You look for the max and mins, which give you the critical points, and then you work from there. When we go backwards, which is happening here, so right, I'm giving a derivative. I want the original function. Now, like I said a little earlier, there's actually many answers to this. But when you go backwards, we're going backwards, right? So let's think about going backwards. We find the max and min, and those are our critical points. That's the first thing we do. Well, in this case, right, we're going backwards. So our zeros, right, all our max and mins and inflection points. Right, just like we did before. Right, first thing we found is our max or min. Those are zeros. So if we're going to go backwards, we're going to find get our zeros, and that's going to be our max and mins. So like if I was looking at this one, I'm going to find my zeros first. So like right here at -6. Right, so I have x equals -6. Now I got to decide if that's a max or min. Well, notice how it's going from negative to positive. So this is a min. So the idea is you have a min at -6. So somewhere at -6, draw a min somewhere. Doesn't matter where. Let's say down here. Right, and then let's go to the next one. Oh, -1-ish. At x equals -1, I go from positive to negative, so that's a max. Positive, negative, max. So at -1, somewhere, again, it doesn't really matter where, this can't be below that, but somewhere around here should have a max somewhere. So again, I picked a random spot, it doesn't matter where I put that, it's just one answer, there's many different answers. So right there. Then we get our other 0, like at 5. And we get to decide that's a min or max. And again, we're going from negative to positive. So down then up. So it's another min. So at 5 somewhere, you can draw a min. So right, it doesn't matter where. So something to that effect. And then all we do now is fill it in. So, okay, well, this has to be going over here. These have to connect. These have to connect. It goes over there. I should have connected this middle part better, but that's the idea, right? That's an answer. It's all about finding the zeros. Zeros are your max and min. Put those, and then just kind of connect the dots. So that's how you go. That's how you go from a derivative to like one level up. Let's do another one to make sure we got the last one we're doing today. Then I promise I'll stop talking. So this one right here. Again, here's the derivative. I want the original function. So we gotta think zeros all are max and min. Stationary flexion or stationary flexion. So here's a 0 at -3. I'll do what we always do. We always like, let's make a sign chart. Let's make it a sign chart because it's a derivative. And then we have another 0 here at 1. Right? Before -3 is a positive. After -3 is a minus. And after is a negative. So at -3, I have a max. So again, somewhere on -3 doesn't matter where. Draw a max. You can do it down here, you can do it up there, it does not matter. Draw max. At 1, I'm going down and I'm going down again. So I have a negative stationary reflection. So at 1 somewhere, draw a stationary reflection. So it's going to kind of go like, that's connected to that one, so kind of like this and then kind of like that. Right, kind of connects cubed. Right, and you know it has to connect to that one. And that's kind of the idea. You go, okay, I got those. If you really want, you could add in the fact that this is a max, so that should be an inflection point. So there should be an inflection point around there somewhere. But that's just a bonus. Really, you just got to connect the dots. Something to that effect. And that's how you draw the derivative. That's how you go. That's how you draw the derivative from the derivative. That's it.